Hey, this is Horner. We're going to take a look at the answers to number 25.18 and 25.19, the two quick checks. We have a typical analog cell phone has a frequency of 850 megahertz and a digital cell phone with 1950 megahertz. They want you to compare the two signals. And so the first thing you probably need to do for each one is find out what is the energy. So energy is equal to HF. So H is 6.63 times 10 negative 34th times 850, and you can do the math, and you'll see that this one will have lower energy, so we're going to make a smaller e, and this one will have bigger energy. So that was pretty simple. Small energy for the analog. And compared to the signal from the analog, the digital signal has higher photon energy. So I know I can cross off letter A and letter C. The only thing that some people do is they go, oh, but wait a minute, let's pick this answer because it says longer wavelength. Well, this one does not have a longer wavelength. It has a higher frequency. And remember, the speed of light is equal to wavelength times frequency. So here we know that wavelength then is equal to the speed of light over frequency. These have an inverse relationship. So even though this has a really high frequency, it has a really small wavelength. And this one has a very low frequency comparatively, so it has a really big wavelength. So your answer here has got to be letter D. It has to have a shorter wavelength than 1950 megahertz, and it has to have higher energy. So that's kind of how that one works. This one's a little bit different. This one, they give you a radio tower that has a certain power. So this is power, and it has an AM signal with this frequency and an FM signal with this frequency. So obviously the energy per photon is higher in this one and smaller in this one, just based on E is equal to HF. But they're not asking about the energy per photon. They want to know how many photons there are per second. If you remember, power is equal to work over time, and work is just the change in energy over time. So here, this would be 50 joules per second. So that's the amount of power each one of these signals has. Let's do this. Let's find out using E for AM, energy for the AM, and energy for the FM, what the energies of the two are. If you do that and you multiply H times F, and I'll let you do that on your own, you end up with 5.64 times 10 to the negative 28 joules for every photon. So that's joules for every photon. But that's not photons per second, so be careful. This next one is 5.64 times 10 to the negative 26th joules per photon. We want to know which one has more photons per second. To do that, what we'll do is we know that from up top, if you have 50 joules per second of energy and you divide it by the 5.64 times 10 to the negative 28 joules per photon, you'll see that the joules cross off and you're left with photons per second. And this one's going to be 8.87 times 10 to the 28th photons per second. That's for AM. And then for FM, we're going to do the same thing, 50 over the 5.64 times 10 to the negative 26th. And that one will be 8.87 times 10 to the 26th photons per second. So that's why the AM signal has more photons per second and not more energy per photon. So hopefully that helps.